So here are our three exercises. We first look at ezsurf and how that is composed actually using the surf function in a specific way. We then comment on the partial derivatives. How do we get these matrices which are only there for exercise today, but in the next session in 2 weeks from today, we can then actually see how it is used to deal with specific models and how information related to mechanistic models can be obtained using partial derivatives. And finally, we look at a specific rate law. It's one that's not discussed in so much detail as we're going to do it here in the materials, but you will find it, if you understand what we're doing today, you will find it easy to apply to do the assignment with respect to the second part of the biological examples. All right, that concludes the introduction, and we go into our first exercise. And for this exercise, I then stop showing our video so you can concentrate on the screen. And I'm going to hand over to Rob to open a script file and get us going on ezsurf.
Okay. So file. Here's our new script file. We always need to save these, so let's save it to the desktop. ezsurf script. We've had some difficulties naming things the same things as functions before, so we found it very useful just to include the word script on all of our files so that we don't get that clash of names. So we save it to the desktop. Okay. If I make that smaller, we can see our MATLAB desktop window at the same time. So what's the first thing, Gerald?
First thing would be to have a look at the function meshgrid, because this is one of the functions that is used within ezsurf. We're going to see later how that works, but let's take a look at meshgrid alone in isolation. What is meshgrid useful for?
Okay, well, let's have a look. So what's it expecting? Well, I happen to know it's expecting two lists. So let's give it some small lists to start off with. So 1 to 3, and maybe 4 to 7. Okay? They're just small lists.
And first, we have to explain why do we need two lists. The reason we are looking at this is because we want to plot a function that is a function of two variables. Right? Previously, we have made functions that were functions of a single array. We have defined that array and plotted the function as a function of this array. But now we want to have a function that takes in two variables as arguments, and that's why we're opening up our meshgrid. So if we do this, that the first entry 1 to 3 would correspond to our first variable.
Yeah.
And the second 4 to 7 would correspond to the values taken by our second variable. So now, what would that give us?
Okay, well, let's run it and see. Okay, so that's interesting. So it seems to have given us 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3.
That's our first thing. So we have the numbers 1, 2, 2, 3 repeated 4 times. So what is 1, 2, 3? If we look into meshgrid, 1, 2, 3 corresponds to our first variable. So our first variable can take values 1, 2, and 3. And why has it repeated that 4 times?
Well, 4 to 7 is a 4-element
right, because we assume our second variable to take values from 4 to 7. So we have that actually 4 times repeated because we can take the second value 4 different values. So we need to have the same thing 4 times repeated. Now, how can we see our second grid, so to speak?
So we're going to have to make this be assigned to two lists. So we can do that the following way. Okay, so now meshgrid is outputting to both AA and BB. Should we see what happens? Okay, that looks better. So now we have our first output as before, so 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. But now BB is assigned to 444, 555, 666, 777.
Right, now you can see that these both have the same dimensions. Both are 3 by 4 grids, or 4 by 3 grids, I should say more precisely. And that helps us to define the values of the first variable and the second variable, AA the first variable, BB the second variable, both on the same grid.
So if you notice here, the first row is 1, 2, 3, but the first column here is 4, 5, 6, 7. That means if we combine AA and BB, we get all the combinations of our first list and our second list. So 1, 4, 2, 4, 3, 4, 1, 5, 2, 5, 3, 5, and so on.
So on. So we can have the first variable for all the values of the second variable. Right. Another way of doing mesh grids of not necessarily natural numbers as we have them here, but of arbitrary intervals, is to use a function called linspace. Can you introduce us briefly how to use linspace?
Okay, so linspace gives us a number, which we can define, of points between two values. So I'm going to call this DD. Linspace. Our first value is the start value, our second is the end value, and our third is the number of points in between that. So let's try this. Okay, if I click run. Okay, so that's given us 1, 2, 3, 4, 5 elements between 0 and 15, evenly spaced.
Right, so in this case, we don't need to worry to calculate the values in between, but linspace will just divide this interval between 0 and 15 into as many intervals as we want to have. So what if we wanted to have 50 intervals?
Okay, then we just change our 5, which is the right variable, to 50. And click. I'm going to clear our screen and run.
So now we have the values for starting from 0 up to number 15, which is the upper limit, but now we have this divided into 50 different intervals, so we get out 50 values, as you can see on the left-hand side in the control window. And that is useful because we then don't need to calculate the distance between things. We can just say how many values do we want to have. So we can make our grid with arbitrary dimensions. Now, let's combine the two. Let's use the linspace command to make a very specific grid, namely one that goes from -2 to 2.
Okay. -2 to 2. How many elements?
Let's just take 50 elements,
okay,
as we have it here, and put that into the mesh grid.
Do we need a second argument this time?
We don't need a second argument if both dimensions are the same. So let's assume for the sake of simplicity that both variables will have the same dimension. Both variables will go from -2 to 2, and both should have 50 intervals, or 50 numbers, actually it's intervals between them. And we want to have that mesh grid output into two different entities.
So let's call that x and y this time.
For example, x and y, if this is our two variables that we have in functions, mathematically x and y is a convenient way. Everybody knows that these are the variables. So what will this output now?
Okay, I think this is going to be quite big. So yeah, that's...
So the question now is, or maybe...
So that's not very helpful. It's quite a lot of numbers.
That's too many. Maybe can you do it only with 5 values for each? Maybe that's easier. And we can see, yeah, that we can see. X goes from -2 to 2, and similarly y goes from -2 to 2. And so we have now a grid defined for both variables that helps us evaluate the function for all possible combinations of these two variables.
Okay, I'm going to make that back to 50, and then I'm going to comment out that line so we don't get that appearing from
time. Right, so we can now use this. This has set our grid, and now we can define a certain function on top of it. Let's take a squared function as is in the materials. So let's assign it a value, maybe z if we have x and y taken already. So how would you now define that function on top of this grid of x and y's?
Okay, so we want to operate element-wise on each of the elements in x and each of the elements in y. So therefore we need to use the functions with dots in front. So if we're going to take, for example, x squared, we need to do x dot upper caret 2. And so we want the same with y dot full stop upper caret 2
So that would be x squared plus y squared.
on each of the elements.
Both variables used, x and y used, both are nonlinear. And we have it assigned to the function which is z, which is now our function of two variables.
Yeah. So we could output this, but I guess it's going to be a lot of numbers again. So how about we plot it instead?
Right. Let's just take a plot. How would you plot a function that is based on two variables rather than just one? MATLAB offers a convenient plotting function.
So instead of using just plot or anything similar, we need to use this surf command. And we just give it x, y, and z.
So that plots our function z, which is the third argument, as a function of its two the variables, which are x, the first, and y, the second argument in this function.
So let's run this. If I make this window bigger. So we can see that this is our three-dimensional plot of the system. And actually,
Okay.
MATLAB's quite fun, so we can click on this sort of rotate button on the toolbar, and then we can rotate it to our heart's content.
Okay. So why have we introduced all these details now? You can see that the function looks fairly good and is what we expected to do. The reason why we have introduced is to show you what goes on in the background if you use, as suggested in the materials, a function called ezsurf. Maybe we can just do it. Can we just...
Okay, so I'm going to close that. I'm going to comment this line out so we don't get that plot appearing. And then we've got this new function called ezsurf.
How does it require the input here? There's a certain convention that we need to follow.
Okay, so here we go, giving us a sort of example, so we need to give it a function. So we're going to give that in quotes.
Single quotes, yes.
I'm going to get rid of that. So you can give it our variables, so they need to be in uppercase. So x, uppercase. Let's say squared. No, we don't need the period now. We just need upper caret 2. And plus y squared to get the same plot as before. We also need to give it as a separate argument the maximum and minimums.
For both variables.
So minus 2, 2, minus 2, 2.
So that is first the range for the x values, minus 2 to 2, and second the range for the y values, minus 2 to 2 again.
And if we run this, we should immediately get the plot we had before.
It's actually getting the same plot. So MATLAB function ezsurf is a summary of what we have done before. It's a summary of defining a certain grid with certain default values and then using that to plot this function z. The reason why we are showing you this is while at the moment it's convenient to use ezsurf directly, in the next session, which will be having a web support session in 2 weeks from today, we'll be seeing how the explicit use of a mesh grid actually helps us to set up model functions that we will use to describe features of differential equations.
So as soon as you have to do anything quite complicated, it's much more useful to be able to generate the grid this way using
Yeah, it's more flexible. And maybe you can just show us what we have here is you can see that this default value of 50 spaces in linspace is actually what ezsurf uses. So if you want to change that, it's more complicated in ezsurf, and you can do any size of mesh grid using the mesh grid functionality. Okay,
Okay.
so I think this concludes our first exercise. And as said, in 2 weeks, we then take this again and develop it further for use in modeling. Our second exercise will be just a few comments on partial derivatives. So if you have looked at the materials, you have seen that we are dealing with partial derivatives and there's certain ways how to deal with them. So we just take a quick example here how to do this by hand. We're not going to do all the steps for you. It's best if you have a paper and pencil in front of you and do it one by one, but just as a comment, to remind us, if we have a rate function like the Michaelis-Menten function, highlighted here in yellow, often what we want to look at is the derivative of this function. So derivative of this rate with respect to, in this case, the variable would naturally be the substrate concentration S. And we know how to do this. We know how to calculate. If you don't know, please go back because first order derivatives are going to show up frequently during the rest of the materials. So, but now we are looking at functions that are functions of two variables. So let's just assume that in addition to the substrate, we have something called a co-substrate. So that this enzymatic rate depends on the concentration of both a substrate and a co-substrate. And we can, for example, for the easiest case would be to just multiply it with the concentration of the co-substrate. So we would have a modified rate equation that is a function of two variables. Now, how would you get partial derivative of this more complicated thing now? So what we want to do actually is to find the derivative of this function, which is called rate, with respect to ds as before. And if I just copy and paste it, we would also like to have it as a derivative with respect to the co-substrate. So there's now two potential derivatives that we can make. There are two partial derivatives. And one thing you can see is that the second thing is fairly easy. So if we want to elaborate this thing first, so I comment it all, the derivative of the rate function with respect to the co-substrate is of course nothing but the co-substrate multiplied by a constant. Now why would that be? Because if we take the derivative with respect to the co-substrate, everything else needs to be constant. So it's clear that K1 and K2 are constants, but also S needs to be assumed constant for this purpose. Right, so let's do this. So if we do this function with respect to co-substrate, we can assume that this is something like a constant times the co-substrate. And if we take the derivative of a constant times the co-substrate with respect to the co-substrate will just go away. Its power decreases by 1, means from 1 it will go to power of 0, it will give 1, and so we just end up with everything else apart from the co-substrate. So this derivative will just be, if I take away the co-substrate, it will look like this, and we are actually finished. If we want to look at now the second thing, doing the partial derivative with respect to S, this is a more complicated thing, so I don't do all the details, but I want to remind you how to do it. It's a complicated entity that needs to look into what the numerator and the denominator do. So what is the numerator? We need to find an abbreviation here. The numerator is this entity, K1 times S times CO, or co-substrate, and the denominator is K2 plus S only. Given this abbreviation, we can then highlight what we need to do in order to get the partial derivative. It is by writing down the denominator as is. So that would be K2 plus S, but we need to modify it. Multiply it with the numerator and its first order derivative with respect to the variable that we are interested in this case, S. So that's with respect to S. We subtract from it the numerator times the denominator, but now its first order derivative with respect to the same variable, namely S. So that's not yet it. We need to put all this into, say, for example, square brackets. First part done, but it needs to be divided by something else. It needs to be divided by the denominator taken to the power of 2. So the square of the denominator is what we need to write down in this fraction as well.
Am I right? That's called the quotient rule.
That's the quotient rule, as you can find it in any book on differentiation or in any text. It's also in the mathematical appendix in your materials that you can see on the Moodle page. Right, so I'm not going to do all these things in detail, but this is what we need to do. We need to now fill in the corresponding expressions in denominator and numerator, with taking it as it is or as its first order derivative with respect to S, and then work it out. We're not going to do this by hand now. We leave that for you as an exercise, but we're going to stop at this moment with this simple function, and we're going to look at a more complex function and have this very same rule applied to a more complicated rate function that we'll be interested in analyzing.
But I think we should let MATLAB do all hard work for us, don't you, Gerald?
Good suggestion, because as we'll see, the outcomes turn out to be quite lengthy expressions.
Okay, so I've been given a new script. Okay, so I'm just going to move this to the right side of my screen so I can see everything. Okay, so I've been given this new rate function. So the rate is equal to a constant times the substrate, but that's divided by another constant plus the substrate plus another constant times by the inhibitor squared. So
what kind of kinetics is that supposed to model?
So it looks a bit like Michaelis-Menten, but with the addition of an inhibitor.
Right, so if that inhibitor was absent, if I was equal to 0, we would just recover Michaelis-Menten, the one that we saw previously. There's no co-substrate now. You can even take a look if you like, but here we just assume that if inhibitor is present, inhibition means that the denominator is increased. So by multiplying it with a certain constant, the overall quantity in the denominator will be increased, so the rate will be less. And we have a specific power of this inhibitor, which comes from many empirical observations where this is supposed to model what goes on in some of the enzymes. A specific example of this type of inhibition might be hexokinase, as it's found in brain tissue. Okay, so let's go and take a look at this more complicated function now.
So we want to do exactly as we did, as Gerald just showed you. We want to differentiate this rate with respect to both S and respect to I. So first of all, we need to tell MATLAB what this function is. So we're going to do this symbolically. So first of all, we need to symbolically define what S, I, and the rate constants are. So we use the command sims. We tell it S, I, K1, K2, K3.
Everything that is used to compose this equation is defined as symbolic variables.
Then, well actually, this is already in a form that MATLAB should understand, so we can just copy this rate down here. So again, the rate is equal to K1 times by S the substrate, divided by K2 plus the substrate plus K3 times the inhibitor squared. Okay, I'm going to comment that line out so we don't get that appearing every time. So now, what do we want to do? So we want to differentiate this rate with respect to S. So we want, let's call that ds. And MATLAB gives us this useful command called diff, to which we need to supply the rate and the variable we want to differentiate with respect to, S. Should we give that a whirl and see what happens? Okay. If I can make that bigger again. Okay. And I'll make this window.
So what does that look like?
So it's quite hard to see. We've got something of the form K1. It's too hard to see, so we need to do something. Let's simplify this. So MATLAB gives us this useful command called simplify. So let's call it the same thing, but let's apply simplify to it. Okay, does that look good?
Yeah.
Yeah. And let's run this and see what happens. I think that's a bit better.
Slightly better. Let's take a look. It's still a fairly complicated function, right? So you can see that by putting in this new thing now, we have a fairly complicated thing that includes K1, K2, K3, I, and S. So all of the things that we started with are still there. We remember that K1 to K3 are parameters, are fixed values, but I and S are two different variables for general purposes. When we have subjected to the partial derivative now, we have assumed that I is a constant.
Yeah.
So we can now take a look at the other possibility.
Okay, so we want to find out what with respect to I is. Okay. So di equals, let's use the same function again, so diff, give it rate, but now let's say we want to differentiate with respect to I. And should we simplify it again just to make sure it's understandable to some extent? Should we see what that runs as? Okay, we've got something quite complicated again. Again, the denominator is the same as before, but the numerator is now different. So it's a multiple of K1, K3, 2, I and S.
And notably, this derivative has something in front of it that we didn't have before, namely it's negative. So we'll see it also later when we plot it. Negative meaning there's now a negative slope. Because derivative means we're looking at the slope, so we'll have to look at negative slopes when it comes to respect of the inhibitor. Okay, that basically summarizes our general differentiation where we have not made any assumptions about K1, K2, or K3.
So the next thing I think to do is to add in some specific parameter values. And the reason we might want to do that is, although this gives us a very general solution, it's actually quite hard to see what's going on.
And we can't plot it in that way because it's all symbolic. So in order to make a plot of it, which is one of the assignments that you're supposed to do in this session, we need that more algebraically, and we need to fill in specific values for K1 and K2 and K3.
So let's do this here. So let's change our script here to have K1, K2, and K3 be some number. So the first thing we need to do is we can take it away. We can remove K1, K2, K3 from the symbolic elements of our script. Now we need to define them explicitly. So K1 equals 10, K2 is 0.1, and K3 as 0.1, just giving the values.
They're just arbitrary values for the sake of demonstration. This is where you then will have to fill in whatever you assume about this kinetics.
So as I said before, I've just removed these from the symbolic elements and given them explicit numbers as values. So we should be able to run this again. So if I can comment out our two lines here and here, we should be able to see what ds and di are now as a function of these numbers and s and I. Shall I run that? I'm going to clear this screen first. Okay, so maybe that's a little bit easier to see what we're doing.
Okay, now we have similar to before, but we have replaced values for K1, K2, K3 by numeric values. And we can see that the variables left are now I and S. So here we have a function of two variables, And with these numbers filled in, we can actually go about then thinking how to plot them in a way that is meaningful for interpretation.
Okay. So in MATLAB, one thing we could do is just to copy this string across and define a function with it. But that's a little bit unsatisfying. What I think we'd like to do is use the value of ds itself to define a function. If you were with us the other week, we did that using a function called MATLAB function. And that gives us from a symbolic description, so this is a symbolic description of ds, that gives us an explicit MATLAB function. So we're going to do some plotting now. So let's make a new function. So we're going to call this fds. And so this is using the MATLAB function command, as I just said. And what this needs is a symbolic expression. So I'm going to give it the value for ds that I've just calculated. It needs to know that we're interested in looking at variables. And then we need to give it the variable names that we've been looking at previously. So in this case, it's s and I. Okay?
Right, so that's for the conversion. So we have a symbolic function that is called ds. You can see that on the left side of the screen on top. And now we convert it to an algebraic function for plotting.
So should we see what that gives us when we run this script? Okay, so it gives us something that's quite hard to see, but the important thing is f of ds is now equal to this thing at sign si. So that means it's a function of s and I, and then the rest of the line is the definition of the function, which is identical to the line here, just with a slightly different notation.
Some rearrangement happening there. Okay, so we can trust that this is done correctly. Now, how would we get a means of plotting, for example, this the first order derivative as a function of, say, the inhibitor? If we wanted to see how the inhibitor influences our rate, we could look at this.
So we need to give our variables some default value of s, some default value of the substrate. And the way we can do this is we can define a function exactly like the function we have appearing here, so at symbol si. We just want something that's at symbol I. So let's overwrite the function we've got currently, as it's not a problem. At symbol I, so we're losing the s. We give it the current definition of the function. We need to give it some default value of s, so should we say just 1?
Just put it 1. Assume S concentration equal to 1.
And the only thing is now that we need to make this still a function of I, so we can just put I back into the function. Should we see what happens if I run that?
Okay, so that redefines our function, and we have something simple. fds is a function of I now. Okay, so how can we use this now to plot this function as a function of the inhibitor?
Okay, well we can just use the fplot function, so it's nice and easy. So function plot, give it the name of our function, fds. We need to give it some limits, so let's say 0 to 30.
Let's try 0 to 30, see what happens.
And let's just run this. Okay.
And it immediately makes the plot. So in the interval of 0 to 30 in the inhibitor, so that would be inhibitor concentration on the horizontal axis, we can see what have we plotted? The derivative of the rate with respect to
S.
With respect to S. And we can see that this goes through a maximum. At a certain point, here's the concentration around 0 as it looks. It increases and then decreases. So it means we don't have a continuous function, but we have something that gets steeper first. So the gradient is larger and then less until it finally, we can safely assume that this will fall down to 0.
So recall that this is the rate of change of the rate with respect to the substrate constant. So it's not the original function we had in the first place, but the derivative of that function.
Right, we'll see the original function in the end. We'll take a look edit with ezsurf, but let's take, so this would be corresponding also to what is in the assignment with respect, differentiated with respect to the first variable.
So of course along the x-axis is the concentration of the inhibitor as well, just to make that clear.
All right. So now let's look at the other function. So there's the possibility to differentiate our rate with respect to the inhibitor.
Okay, so I'm just going to comment this out so it doesn't pop up every time. And so now we need to plot di. Okay.
We previously defined that as di.
So that's still on our screen here. So that's the function we're interested in plotting. So that's actually described the moment as a symbolic equation. So we need to again change that into a MATLAB function. And the way we do that again is using exactly the same before. So function of di is equal to MATLAB function. Give it the symbolic description we're interested in, so in this case di. Again, use the command vars and tell it that we've got variables s and I. So
it's quite analogous to what we did before.
So I'm just going to clear this screen and then show you what this looks like. Okay, so that's...
Okay, so we have some complicated algebraic function, which is a rephrasing of the previous symbolic function.
Okay, I'm just going to make some space on the screen so you can see what I'm doing. Okay, so we need to plot this now, but again, we want it as a function of just the inhibitor concentration alone. I think it might be nice if we plot this more than one equation, so I'm not going to overwrite this function as I did previously, but I'm going to make a new function. So f di1 will be a function of just the inhibitor. What I want to give it is f di, some generic value for the substrate, so again 1, and I. So it's still a function of I.
So very similar to previously, just with that we take the other equation. Yeah.
But I'm interested in seeing what happens as we change the value of the substrate.
Right. Now, what would that curve look like for different amounts of substrate present in this?
So I'm going to duplicate that line, make a new function name, and then say maybe we could have 100 units of
For
substrate.
example, 100-fold concentration of substrate, and you can fill in any number, but so we would see the same function, but for different constant amount of substrate present.
So if we want to plot both of these, we need to say hold on, and then we can use the fplot command as well. So fplot, the name of the function, which is fdi1, and then some limits, so 0 to 30, say. But as we're plotting two things, it'd be nice to know which line corresponds to which element, so we're going to tell this that I want it in black. And
Okay.
then duplicate this line as well, copy and paste, change the function, keep the same limits because we want to know what happens over the same range, and then maybe change this to red to see what happens.
Give it a different color. So that would firstly plot this partial derivative with respect to I for a substrate concentration of 1, and then plot the same function with a substrate concentration of 100, which is very similar to what is needed to be done in the assignment when it's thought to make a plot of the derivative with respect to insulin, but for different amounts of glucose, for those who know what the assignment looks like. All right.
So I'm going to make a prediction. Remember that our di was negative, so I think this is going to be less than 0 to start with. But let's see what this plot looks like. If I just click run, make this larger. So yes, I was right. So we start at 0 and we go down generally.
Okay, we go down firstly and then go up and then reach 0. Actually, if you look at it for large values of I, you will see that both go to 0 in the long run. And you can see both curves go through a minimum in this case. Whereas previously we had a maximum, now we go through a minimum, but the minimum changes its position. So the minimum changes is positioned such that it's at lower inhibitor values in the black curve, which we remember was for a low substrate concentration equal to 1. And it goes to larger values of inhibitor, somewhere around 20, for large substrate concentration, which was taken here as a value of 100. So does it make sense? Yes, it makes sense, such that if you have more substrate present, you also need to increase, you need to put in a higher rate of inhibitor to get the same amount of inhibition.
So again, recall that the y-axis is the rate of change of the rate equation with respect to the inhibitor, and the x-axis is the inhibitor concentration.
And so you can see, I think that concludes our analysis of these slopes of the original function. You can see that by doing the symbolic manipulation and combine it with an algebraic manipulation, we can have both explicit expressions for these functions, and we can all sorts of plots. Anything that we are interested in this function, we can look at. Of course, we could also take the second order derivative now with respect to these, which would be 4 possibilities, which we'll see later, but we don't do that now. And we come to our last point, namely, now that we have seen all the things are derivative, now actually we should maybe finally plot our original function. What does this rate function look like? You've seen some examples in the materials. And I think to come to a conclusion for this, we can be much simpler than we did at the very beginning. Rather than using our mesh grid, we can just take advantage of the ezsurf. So remember what the function looks like, and Rob takes it and copies it over so that we remember what we wanted, and we need to change convention. You know that S and I is not the way that ezsurf is expecting these things. So how do we have to input it into ezsurf?
Okay, excuse me a second while I just save this function. So something sensible, ezsr script. Okay. So that's our function, and we're interested in plotting into ezsurf. Remember, before we had to give ezsurf something in terms of our variables in single quotation marks. So we had it in terms of x and y, didn't we?
Yes, we needed to use x and y, and it was capital X and capital Y in addition.
So the only other thing I needed from the previous script, excuse me, was the k constant values. So if I just put those in a comment up here, we know what they were. Okay, so we need to fill in this. So what would it be? It'd be 10. So k1 was equal to 10 times by, should we call s to x? Maybe we should have a comment here. So that s is equal to x, and I guess I would be equal to y.
Okay, then we know which corresponds to which.
And then that's all over k2, which was 0.1.
Defined as 0.1.
Plus the substrate concentration, which was x. Plus k3, which we had as 0.1 as well. And then times by the inhibitor concentration, which is now called y, squared. Recall that we needed to give this some boundary, so the minimum x, minimum y, maximum y. So just for example, let's go 0.5, 0.20.
So that would be 0 to 5 in substrate and 0 to 20 in inhibitor. Previously plotted 0 to 30, we saw that not so much exciting things are happening for larger inhibitor concentration. And it also has the value of 1 that we plotted previously within the range that we are plotting for the substrate concentration.
Okay, so I'm going to run this and hopefully we'll get our nice 3D plot. Oh dear. So we've got an incorrect line. So we've got this horrible error codes, but actually all we've done is we've missed off a bracket on the end of our denominator. Okay, So it said unbalanced parenthesis, curly brackets or square brackets. And I'm going to clear that. And if I run this code now, that's better, isn't it? Okay. Again, we can use our rotating thing to move it about. Okay. But actually, I don't really like those colors. How about we change them?
How can you change the color?
Well, we could use the color map function.
It's just a hint that there's a certain variety of different color maps. If you don't really like the rainbow color map, we can change it to something different. And that has actually a more serious reason behind it, namely that I think in general any research into coloring scientific plots tells you that the rainbow plot should either be avoided at all or be taken with extreme care. And the reason for this is that the rainbow plot, using the colors of the rainbow, using a couple of colors, the observer can't avoid of assuming that a change in color, say from red to yellow, assumes that something qualitatively different is going on.
So something's getting better as you change from red to green, say?
Yeah, something that has to stop previously can go when it's green, but it has to stop when it's red, or something that qualitative changes. If they are not there, it is recommended that scientific plots not make use of such things as all the colors of the rainbow, but make use of something simpler.
The other thing I would say is that, remember, color blindness is quite prevalent. About 10% of men have some form of color blindness. So red and green are not very good, and you should try and maximize the clarity that most people will see.
So
your
one thing, I don't know, we can use different things, but there's one that's called copper. And I think if you just put that in single quotes, it will give a different coloring to it. In this case, a coloring that uses only one shade of a color rather than making it different types of colors. So you can turn this around and you can get some idea of what this looks like.
I'm sure there's a way to find, if you search for MATLAB color maps, then you should find a page with a list of them all on.
You can find a list in the help page for them all, for color map, for all the options that are there. And one thing that I remember is the cool one. You can also use the cool one that shows only two different colors, where we can highlight, for example, where's the maximum rate. If we add a color bar to this and rotate it slightly, we can see what this looks like. And we can try a cautious interpretation of this rate. Okay, if you look at it from this angle here, you get a hint of the Michaelis-Menten function, namely the hyperbolic function that increases and saturates. And that's why, in this perspective, the dependency on X, the substrate, is highlighted. As if you change it around, or the other way around, you can highlight the dependency on Y, and you can see what happens with respect to Y. The slope is negative in all cases, but it's first a very light slope. It's not, if I include maybe an arrow, then the slope is originally something like this. That's a small negative slope. At a later point in this graph, there will be a steep negative slope. And as we remember, that function goes through a maximum, because finally we end up with smaller slopes again, and in the long run it will go to slope 0. So we can actually see how this now reflects the regulation of this enzymatic rate, assumed to be Michaelis-Menten substrate, by the presence of inhibitor. Namely, the rate will be decreased initially slowly, then steeply, and finally it will come to 0 rate and saturate there for extremely high concentrations of inhibitor. So it's a useful thing, because we can then make all sorts of conclusions or predictions about how a combination of substrate and inhibitor in a certain context of, say, experimental or in vivo is expected to happen and is thought to be influencing the outcome, which in this case is production of a certain product, which we have not modeled explicitly. Right, and final remark on this point here is that if you have it in such a form, of course, it's also very easy to test different inhibitor functions. So if this exponent, say, is not squared but is just linear, by just executing the same thing again, you can also see how the shape looks like in this case with a linear function of the inhibitor. And that, of course, is what makes it most flexible, that once you have it written in such a way, you can immediately check all sorts of combinations and say which one fits my experimental data better. And we then think of, for example, pharmacokinetics or the dependency where the inhibitor is meant to be a pharmaceutical that is supposed to specifically inhibit a certain enzyme if you want to have its activity decreased. So you can then put in your experimentally measured rate constants and try to fit to your experimental data and see which function for the inhibitor, which exponent best models the effect that you measure experimentally. Right, that brings us to the end of today's session. So we have looked at very abstractly functions of two variables, but we have immediately seen that within the context of, say, spatial gradients, as in the materials, or what we have done today in this context of enzymatic rate functions that depend on more than one species, that we can conveniently use the surf or ezsurf functionality in MATLAB to plot these things, and use symbolic and algebraic manipulation of the functions to get all the important features that we are interested in this more specific context. If you look into the assignment, you can see that the same also applies for more physiological level of modeling, for example, the endocrine case of blood glucose regulation by insulin.